Amateur astrophotographers around the world can now enjoy taking full control of the Shulman Telescope. As one of the largest dedicated public access telescopes in the United States, the 32-inch telescope was designed from inception to provide full remote control over the internet by astrophotographers worldwide. Note that remote use of the telescope for astrophotography is not the same as live viewing, and is targeted towards individuals interested in acquiring high-resolution astronomical data that have previous experience using photo editing software with raw astronomical images in a fixed format. To purchase time for remote astrophotography with the Shulman Telescope, please visit our website at skycenter.arizona.edu and click on Tickets.
Okay, so a quick introduction. Adam Block will then take over next. He is the founder of the Mount Lemmon SkyCenter, which is up on the Catalina Mountain Range, where we, as I mentioned earlier, we have several telescopes around Tucson. He's been an integral part of many of the Tucson outreach components that have happened relative to astronomy and planetary science. We'll play his video, think of any questions that you might have for Adam, and we'll go into a live Q&A directly afterwards with him. I hope you enjoy, and I'll talk to you soon.
Have you ever seen a beautiful picture of space, perhaps of a nebula or a galaxy, and wondered if the colors are real or how big it appears in the sky? Many pictures of the cosmos are abstract and seemingly far removed from our daily experience. The irony is that pictures of space, they capture that which is most common and ubiquitous. It is our daily life on Earth that affords us such a uniquely special view. You see, the problem is, when looking at an astrophotograph, there are no people or easily identifiable references that help us to orient ourselves. Yes, the abstract form of a nebula can be beautiful without any further consideration. But if you were shown a picture of a person that was green, or perhaps they stood taller than a house, you would very quickly reassess what that picture was communicating. There's a similar kind of skill set that you can apply to the interpretation of astrophotographs, and that is what I'd like to show you. So please come, join me in a journey through space and time, and revel in the mysteries of the universe. We live in a world of images, and our digital lives rely on our ability to interpret them. It is a skill honed by countless hours in front of screens, big and small. However, some kinds of images, especially those that depict tremendous scales of size or time, defy our ability to easily interpret them. These images were not chosen randomly. They exhibit what inspires the most commonly asked question: what is the nature of the sparkles or lines that are emanating from the stars? Some people think that they were put there for artistic reasons. Others do not question their appearance in photographs because it perhaps meets an expectation of what a star should look like based on drawings or cartoons. These patterns are indeed artifacts produced by certain telescope designs. Reflecting telescopes that use mirrors have structures that hold secondary mirrors or other instrumentation. These rods or vanes obstruct a small amount of light that enters the telescope, and through a process called diffraction, the light rays are scattered. These so-called diffraction spikes are not desirable, and some form of diffraction always occurs with any obstruction. The images shown so far were produced by this telescope. This is the Shulman Telescope, and it is the primary telescope at the UA Mount Lemmon SkyCenter. This telescope is available to take images with, just like the ones you've seen so far. You can see the vanes that support the secondary mirror of this instrument. Notice how in this image, produced with a telescope that uses only lenses, there are no diffraction patterns. There are no obstructions to cause it. Most large telescopes use mirrors because it's not advantageous, or in many cases even possible, to build telescopes made only of glass lenses. This is why most professional images have diffraction patterns. On a more philosophical note, notice how the light of stars is spread into a spectrum of its colors. The diffraction of light into its component wavelengths is the primary way most astronomical measurements are made. Even though these are artifacts, the fundamental information is literally encoded in these images. It's as if the universe wants us to discover the answers if we only look hard enough and ask the right questions. Scintillating diffraction patterns are only but a superficial element of astronomical images. There are much deeper considerations of what is recorded in a picture. Typically, CCD cameras that are optimized for astrophotography are very sensitive and can record tens of thousands of discrete brightness levels. Computer monitors, by comparison, only display 255 grayscale levels. An astrophotographer must then choose how to represent and render the data recorded in an image. This is a picture of a wonderful spiral galaxy, and although its splendor is recorded in the data, those values are being rendered in its unstretched form, with a monitor only displaying the very first few hundred brightness levels. By changing the white and black points, more of the data can be visualized. Now, we see a galaxy in the center with some spiral structure, as well as a few other background galaxies. Finally, by representing the data in a non-linear way, the very faintest details are displayed proportionally brighter than the other parts that were already bright. However, even more of the story of this field is revealed. Now, we see the faint spiral arms as well as tidal tails of other interacting galaxies. When looking at an astrophotograph, keep in mind that the person who creates the image consciously decides this element of representation, as well as many others, as we will see. Blend in the color information, and the image takes on new dimensions of life. Notice how I chose to display the very faintest and noisiest features as delicately hinted. This communicates that those features truly are difficult to see relative to the other elements of the image. The colors represented in astrophotography come in a few major variations. The images that you've seen so far in this video all record the visible wavelengths of light. However, this is only a small fraction of the electromagnetic spectrum, and astronomers pursue the entire span of energies that can be detected with instrumentation. With regards to the light we perceive with our eyes, even if looking through the largest telescopes in the world, the universe would not appear with the vibrant colors shown in these images. Our biology is simply not designed to detect these minuscule quantities of light. A full color image of visible light is created with a camera using filters that discriminates between reddish light, greenish light, and bluish light. These pictures are called broadband images, and when the images are assembled, the colors of light are mixed together in a way that is analogous to what our brains do. So in a picture like this, I do not choose that this should be blue or this other area be red. If your eyes were as sensitive as the camera that was used, and you could expose for as long, This is approximately what you would see. Sometimes people ask if an image such as this is enhanced in terms of its color. I take a different perspective and explain that it is our view of the universe with eyeballs which is diminished. If you look through any telescope in the world at this object, you would not see any color in this nebula. Yet, red and blue wavelengths of light would truly be hitting your eye. In this sense, then, this picture isn't an enhancement, but a more accurate portrayal of reality. And these instruments become our surrogate senses that allows us to understand the world around us. Another kind of color representation is done through narrowband imagery. This method captures light of specific wavelengths, which results in a high contrast image of nebular features. However, this isn't a true full color image because all of the other wavelengths of light are just not included. Here is a broadband image of the Eagle Nebula with the very famous pillars of creation in the center. These pillars were made famous by the iconic Hubble Space Telescope picture of them. The HST picture is a narrowband image. Note that the wavelengths that were used were only one green portion and two red parts of the spectrum. These then were mapped as red, green, and blue, resulting in a mapped narrowband image, which is an arbitrary color assignment. As you can see, the HST image of the Eagle Nebula is a small portion of a much larger object. This leads us to the important ideas of resolution and field of view. When looking at an astrophotograph, each pixel of a sensor detects light from a small patch of the sky. The size of this area on the sky determines the finest possible resolution of an image. First, a quick review of angular dimensions. A degree, perhaps the size of your fingertip held at arm's length, can be divided into 60 arc minutes. The moon subtends roughly half a degree on the sky, so it's approximately 30 arc minutes across. A crater on the moon might be several arc minutes in size, and an arc minute can again be divided into 60 arc seconds, so a bump on a crater on the moon might be of this size. Taken together, the array of all the pixels determines the full field of view. The HST picture of the pillars is only a few arc minutes in dimension, whereas the field of view of the picture taken with the Shulman Telescope is 10 times larger, though this is still smaller than the diameter of the moon. There is something deceptive at play here, though. Each pixel of the HST image subtends a tiny 0.05 arcsecond squares of the sky, whereas a pixel in my image covers a patch of sky that is 6 times larger. Before I show a one-to-one comparison, there are some important rules of thumb to know about optical astronomy. First, stars are so far away that they are not resolved and are truly points of light. However, as light passes through our atmosphere, the rays are deviated by small amounts. We live in an ocean of air, and our view of space from the ground is blurry. Typically, this blurriness smears images by 1 to 2 arc seconds. Now we know enough to start interpreting images of all sorts. Let's begin with this wide-field image of the region of sky near the Orion Nebula. This image was acquired with this astrograph. Each pixel at the back of this telescope sees 5 arc seconds of sky. Recall that stars are points and the atmosphere blurs images by 2 arc seconds, which is smaller than 5. This means that the stars in this image look like little pixelated squares. The special name for this situation is called being undersampled. Now we overlay the region of sky captured with the Shulman Telescope of the Orion Nebula and zoom in. Due to the increased scale, we can clearly see more details. and the stars are now blurred across many pixels. Finally, we can overlay the HST image and see things at its intrinsic resolution. The stars are nearly pixel-like and undersampled again. The fine details here are due more to the fact that the telescope is above the Earth's blurring atmosphere than it is due to the optics of HST itself. Did you notice that the HST picture is not a full-color image? One giveaway is that most nebula that have glowing clouds of hydrogen gas are pink or red. Other variations with multiple pastel hues are a good sign that the image is composed of mapped colors. Another thing to consider is that we now have two images with stars that are undersampled, both the wide field image and the HST image. So how in general can you tell the difference? The easiest way to know is to look at the size of features of the object. If they are large compared to the field of view, it is most likely a large or space-based telescope image. Wide field images will have small stars and also small details. Finally, no matter what kind of astrophotograph you're looking at, the stars in the image will appear to vary in their size. Stars are points, but all telescopes, even the ones in space, create images in which the light is spread out due to diffraction. The brighter the star, the more of the scattered starlight you see. So sizes of stars in a given image only signify brightnesses, not true dimensions. Take, for example, this wide-field deep image of Betelgeuse. This star actually fits inside 1 pixel on this sensor, but the bright glow of the scattered light can be seen to spill across hundreds of pixels. Let us use our skills to identify a few different types of images. First, we'll start with what might be a tricky image. This is a broadband image of one of the most colorful regions of the sky. Basically, each nebula type is shown here. There is red emission from glowing hydrogen gas near the star at the right and more of it in the lower left corner. The top of the frame is dominated with bluish scattered light from dust. This is called a reflection nebula. Finally, dark clouds of dust obscure the view, except where they thin, and then they show golden hues of light that filters through them, especially near Antares, which adds some of its own yellow-orange light. This is literally the palette of a large majority of diffuse nebulae. Can you tell if this is taken with a large telescope yielding a high-resolution image, or is this instead a wide-field image with undersampled stars and lower-resolution details? If you said this is a wide-field image, you got it right. This is a 4 by 8 degree region of sky. You could fit 64 moons in this field of view. Galaxies such as these are so far away that only our imaginations can span the distances. As such, when we look at galaxies, we see great averages of information. The combined light of stars and nebulae create low contrast details and colors because this light is mixed together. For this reason, it's unusual to see mapped colored images of galaxies, except perhaps for those that are our nearest neighbors. Here is a broadband image of M82 with an enhancement in the H-alpha emission that corresponds to the color of the red filaments of gas being expelled from this star-burst galaxy. The colors are the same without the enhancement, but by adding more signal for this particular feature, the added contrast makes the image much more compelling. When mapped colors are employed, the result is obvious and can highlight structures of galaxies. Here, radio wavelengths of light, mapped as blue, trace cool molecular clouds of hydrogen gas and show the skeleton of the galaxy. Here's what a regular broadband image of the galaxy looks like. This is a full-color image of what is effectively a narrowband object. It's a dying star that's lost its outer layers of gas. Our own sun may eventually end its life billions of years from now in a similar way. The sphere of gas fluoresces this characteristic blue-green color due to small amounts of oxygen in the nebula. This process always yields this particular color, which is why the HST picture of the same is an example of a mapped color image with its expected extraordinary detail. Here is another image. Is this a mapped color image? How about the resolution? What kind of telescope likely generated this data? Well, this is definitely a mapped color image, and note that the details are quite large. The difficulty is that many images are not posted at their intrinsic resolution. Even an HST picture, shrunk down to some small size, can look like something a small telescope from the ground can do. But when the full image is shown, the image characteristics become obvious. Finally, how about this image? This is another mapped color image, but this time it really is a wide-field image taken with a small telescope. While the colors and resolution of an astrophotograph are generally image attributes that can be seen directly, many other aspects of processing that take place to produce an image are not obvious. Certain kinds of digital processing leave characteristic artifacts or other telltale signs. However, the important idea is that images of space are not snapshots. Raw data is typically dark, colorless, and perhaps even uninteresting. An astrophotograph, then, is the sum of hundreds of processing choices that are made to render the final image. Given the same data, different people will end up with different results. I would like to highlight just a tiny few such considerations to give a taste of what these decisions look like. When the initial raw data is displayed, it's possible to identify colors or details that are desirable to have represented in the final image. Many processing choices will blunt that effort or make it an even unattainable goal. Seeing the final image in your mind and processing the data in small methodical steps helps to stay on course. In this particular image, each of these features were observed early on, and with each processing step, they were maintained so that they could show up in the final result. CCD sensors produce linear data that exceeds a monitor's ability to be able to display everything at once. And so non-linear ways of displaying tonal variations are crucial. Without the use of high dynamic range algorithms, the interesting features of this galaxy, NGC 5866, could not be displayed. Note the inner disk with bluish tips and thin dust lanes, as well as outer distortions in the galaxy's halo. In fact, these kinds of decisions are not unlike what Ansel Adams would make when he adjusted the tonal values of his images. What interested him was not what he saw through his camera's viewfinder, but instead what he pre-visualized in his mind as a final image. He would then dodge and burn his film to achieve his vision. With astrophotographs, typically these adjustments are applied globally, or, if selectively, they are conditionally applied based on thresholds of brightness, color, and contrast. High contrast in particular is an image attribute that is preferred by both image makers and image viewers alike. There is an ancient evolutionary preference for high contrast, and this preference is shared cross-culturally. Adams, of course, knew this and played with it in his photography. The same lessons apply in astrophotography, but with some caveats. Take this image of the Trifid Nebula. Which version do you find most compelling? There's no right or wrong answer. These are simply just different choices. However, there are consequences for the choices that are made, and that is something to be appreciated. If you did not guess, my image is the one on the left. Although I could cater to the sugar high that contrast gives, I don't, because it comes with a cost. Light that filters through the clouds of dust has a subtle attenuation and depth which I feel is lost and flattened with the opaqueness that high contrast creates. To me, there exists truths in astrophysical objects, and I enjoy communicating as many as are captured in the data. For example, here are 3 images of the famous galaxy NGC 7331. This galaxy features wonderful dust lanes in its disk that reach all the way to the center. With particular processing choices, it's possible to display the dust lanes all the way to the core, clearly and distinctly. But to me, the cost is high. Galaxies truly are brighter in their centers compared to their outer disks. Maintaining this truth, and at the same time showing as many dust lanes as possible, that's my style. This means that although I show the dust lanes, they are more difficult to see in the center due to the lack of contrast. But to me, this is exactly what I would expect when looking at something very bright. In another example of the same sort, I processed this galaxy, NGC 4698, with my processing and then a version of high contrast on the right. But I prefer my final result on the left. I think it, again, better communicates the overall nature and features of this galaxy in a natural-like way. Here, I stand in front of what at first appears to be a relatively nondescript picture of space, but one of the very best astrophotographs ever taken was of an object hidden within the inky blackness of this field of view. In fact, to appreciate just how superlative this picture was, we'll use some of the lessons that we've learned in this video, as well as find our place in the universe. To travel to the large distances that we need to, light speed is necessary. Light, in a particular unit of time, travels a particular distance. Take, for example, sunlight. It takes 8 minutes, approximately, for light to make it from the sun to reach us here on the Earth. So we say the sun is 8 light minutes away. Now, if we wanted to use the all too terribly small Earth-like units of miles, we can say that the sun is around 93 million miles away. But those numbers become unimaginably difficult to keep track of. Light units are much better and more convenient for measuring distances, large distances in space. Take the size of our solar system, and I'm going to be generous here and say the interesting parts of our solar system might be around 1 light day across. So it takes about a day, 24 hours, for light to make it from one side of our solar system to the other side. And what I'd like to do is create a model that allows us to appreciate how far away the nearest stars are, how large our galaxy is, and then where other galaxies are. I'm going to use something common like a penny to do that. So this penny, I'd like to squish our entire solar system 1 light day across into the size of something 1 centimeter or so across. Penny is a little more than a centimeter in size. But imagine this is about right. So you would have the sun at the center here with the Earth, all the planets, everything you know and love orbiting about this penny area representing our solar system. At this scale then, we can begin to imagine how far away the nearest star is. Its name is Alpha Centauri, and it's 4 light years away. Well, if this is 1 light day, then a light year is going to just be 365 of these. That's about 3 meters away, because each of these is a centimeter. So I need to do 4 times that in order to get out to the nearest star. And that would be roughly 12 meters away, a little more than 30 feet or so away. I think you can begin to imagine that if this is our solar system, already things are starting to become relatively large, because imagine you wanted to describe the size of our galaxy. We would only need to know 2 numbers. We just need to know how many stars are in our galaxy. That's how many pennies I would need to have in order to build a model at this scale. And we would need to know how large the galaxy is. Well, our galaxy contains more than, but at least, 200 billion other stars. So if I'm going to build a penny galaxy, I would need to begin with 200 billion pennies. If I had 200 billion pennies, I'd be a happy guy. That's a lot of money. There aren't that many coins in circulation in the United States, so this is in our imagination. And Our galaxy is on the order of 100,000 light years across. So with that in mind, we can start to build any galaxy. We just need to know what is the average distance between stars. Our nearest neighbor is 4 light years away, but let's say that it's only 2 light years are necessary, so 6 meters or so. So maybe 10 feet to 15 feet or so is the spacing of pennies that I would need to set out to represent the stars of our galaxy. And I would do this one at a time. It'd take me a very long time, and spread it out until I've got an entire galaxy of pennies. How big would that be? Well, 100,000 light years across. If 1 light year is 3 meters, that's 300,000 meters. If we wanted that in kilometers, then that ends up being 300 kilometers in size. So if our solar system is this large, our galaxy extends 300 kilometers in scale. And that's the beginning, to give you a sense of where we are. And then we would like to go beyond to consider where other galaxies are. Our nearest neighbor is the Andromeda Galaxy. It's located 2.5 million light years away. So if I continue with this model, I still end up by describing where other galaxies are off the Earth, even if I make our solar system only this large. The Andromeda Galaxy spans this image of nearly 4 degrees of the sky. If you were over there looking back at us, this is how we might appear, though I'd like to think that we have the better spiral arms. The stars you see in the picture are all in the foreground and part of our own galaxy. Zooming into the center reveals dust lanes that swirl all the way into the nucleus. Note that I was not too aggressive with the contrast in order to communicate the brilliance of the downtown galactic center. We live on the outskirts of what is the Virgo cluster of galaxies, the center of which is located some 40 million light years away from us. And that is what this is a picture of. This is a wide field image of that part of the sky that contains thousands of galaxies, though they're hard to see at this scale. You can see some of them, though. If you look at this general area, you'll notice some fuzzy oval patches. Those are all galaxies. And in fact, this general area is towards the center of the Virgo cluster. Let me turn on a label or annotated view of this region of sky, and I think that you can appreciate just how many galaxies there are in this particular field, thousands of them. In fact, you can see somewhat of a gradient of galaxies going from this part of the picture on to over here, where it is much higher concentrations in this general area. So that gives you a sense of the number of galaxies, and I've been fortunate enough to have been given the chance to take pictures of many of the galaxies in this part of the sky. When you do so using a larger telescope, you're able to see them in much greater detail. For example, this is M100, probably one of the brightest and most beautiful of the nice symmetric spiral galaxies in the Virgo cluster. And when you show a large image of it, it really is a beauty to behold. Here is what at first appears to be a single little blob, but when you zoom in, you'll find that there are a pair of galaxies too, an elliptical galaxy as well as a spiral. My favorite galaxy in the view is M58, which is just, I think, an underappreciated spiral. We'll also find that there is M91 and M88, and those are also some beautiful spirals. Just a word about the spirals. You'll notice that as you go across the field, there are more elliptical galaxies in this area than where I've been pointing to where all the spirals are, because as the galaxies orbit closer to each other, they tend to mess up gravitationally, they affect each other, and they mess up those spiral patterns. It is in fact one of these elliptical galaxies, the largest of the Virgo cluster, that we will be venturing, because that is where the monsters lie. We are going to be going to M87, and it is the location that we will find what I think is the very best astrophotograph ever taken so far. Magnifying the image more from the Plomenus astrograph to the Shulman Telescope shows that there is something remarkable coming out of the core. It is unlike anything else observed in the local universe. This is a relativistic jet of gas and energy that stretches for tens of thousands of light years. Zooming in more with the HST picture shows the detail in the jet and hints at the fact that there is something monstrous, something very powerful in the core of M87 to create this outflow. The only thing known in the universe that can create this much energy is a black hole. This is what has been assumed, but nary a single example ever directly seen, for decades. If you recall, each pixel of HST sees a tiny 0.05 arcseconds of the sky. If we zoom in to just a single pixel in this image and make it fill 1,000 pixels on the screen, then the center single pixel is the size of the region captured by the Event Horizon Telescope collaboration. This feat required combining the light simultaneously captured from a network of telescopes that spanned the globe. Nothing less than a telescope effectively the size of the Earth could have had enough resolution to capture this region and directly observe the black hole at the heart of M87. This is a mapped or false color image in short radio wavelengths of light. Before the spring of 2017, pictures of black holes and magical unicorns were in the same category. We live in a time when a century-old question, one for which much ink has been spilled, is answered. Yes, there are black holes in the universe, and yes, much of the physics looks about right. The region shown here is roughly a light day in extent. Recall the penny for our solar system shown earlier. And it has the mass of around 6 billion suns. The image is as fantastic as the object it captures. It is the first of its kind, a one-of-a-kind, and an unbelievable astrophotograph to behold.
Okay, so I hope you enjoyed our presentation from Adam Block, an astrophotographer. If you haven't realized or maybe been alluded to, you know, this is an award-winning astrophotographer, so we're really honored to have the Art of Planetary Science hosting Adam Block. Of course, the U of A sphere of astronomy and planetary science is quite large, and so the Mount Lemmon SkyCenter and Adam Block are a part of Stewart Observatory, which are just across what we like to call the Cherry River, Cherry Street being the divide here between the sort of space sciences corner. And so you'll see a lot of Adam's work in monthly columns of Astronomy Magazine. He's been covered by the Daily Star. Several of these images are also featured on the Astronomy Picture of the Day. And so we're going to take a quick moment. So be thinking of your questions now. We're going to take a moment actually to take a peek at the at the Astronomy Picture of the Day, because of course, as you might imagine, it might have something to do with our Adam Block presenter here. So we'll take a view at today's, again, another acronym for us is the APOD, or the Astronomy Picture of the Day. And perhaps I'll actually let Adam take over and answer this a little bit more. So let me turn on his video and I'll let Adam explain this photo while I continue to screen share that. Let's get Adam back in here.
Mute. Am I there?
We hear you.
Okay.
All right.
Can you see me as well?
I don't have your. I'm going to keep it on the APOD, and then I'll switch your
fine.
video after that. Yes,
Yeah, that's fine.
yeah. So I'm going to scroll down since the screen's a little not quite, but we'll get to the top of the feature here, and perhaps I'll let you talk about it instead of you don't have to show
Well,
it.
it's just serendipity. This is an old image. Sometimes the Astronomy Picture of the Day website will recycle images every once in a while, kind of a random thing. And it just so happens that today they decided to put that image. It was just totally random. But it's cool because this image is exactly of the sort that I think ties into the presentation that I just gave, which is offering a perspective. In this case, it is of field of view, it's of scale, to just communicate how large on the sky our nearest neighbor, the Andromeda Galaxy, is. It's very large. If your eyes were really sensitive, you would see that it extends far beyond the diameter of the moon. So this picture is taken using the same telescope, a wide field image using a small refractor, and one picture of the moon, one picture of the galaxy. Of course, they are not like this in the sky, not together. So these are two superimposed images. It is a composite image, but it communicates something that many people are unaware of.
Do you think they chose this for International Observe the Moon Night tomorrow?
Oh, that could be. I don't know how. Yeah, maybe. I don't know.
Follow-up question: How many times have you been in the APOD? Have you kept track or have you lost track? But they keep recycling.
Well, like an astronomer, I can put an order of magnitude. I don't know exactly what the number is. It's something on the order of 90 or so.
Wow. Okay, we like order of magnitudes.
Yeah, there you go. So almost. Well, then I can just say it's 100.
100.
Yeah,
wow.
But it's not 100, but it's something more than 85.
Wonderful. Well, serendipity. How wonderful is that? So
that's pretty awesome. That is cool.
Okay, so we'll go ahead and get these questions up here, and let's see. I'm going to check our Q&A. Could you tell us about how optical physicists can Can you tell us about how optical physics can understand from astrophotography? So I assume what we sort of get between optic physics and maybe testing different optics on different astronomical objects, the interplay between the two, perhaps?
Maybe, I don't know where to go. Ask me that in another way. I didn't understand. So is it the optics or is it what we learn in the pictures themselves as far as the astrophotography? In other words, there's a lot you can learn from a picture, even though you may not be making a scientific, quantifiable measurement. So, for example, you can discover things. You can discover supernova. Maybe, as I did, I discovered a galactic stream of a galaxy that was being ripped apart, a small galaxy being ripped apart by another. And so that might be something of interest to astronomers to study. As far as optics are concerned, though, I don't know.
Yes, or a follow-up question from them. What does the Mount Lemmon SkyCenter have to offer the physics majors? So perhaps more, do optics students or physics majors get to come work with the actual equipment, or have any students built maybe detectors or different optical paths?
I see. So first of all, I think that there are many avenues for students to pursue, especially within the Department of Astronomy, Physics, LPL, and so on, that would give those kinds of opportunities to work with other people and so on. Mount Lemmon SkyCenter, I would say, is probably one of them. There are always opportunities to volunteer. And I think that there are also opportunities where you can shadow or get credit for being a part of the Sky Center. Really, the person to talk to about this would be Alan Strauss. He's the director. And that's who the students should connect with, because there are many opportunities that I don't know in particular. But I have seen in the past that, students have projects. There are opportunities, there have been in the past, where entire classes would go to the observatory and have an experience there. But of course, I would even just go on, go on your own. It's quite an experience just to be up on the mountain and look through that telescope.
Yes, yes, of course. We're virtually looking through our telescope this weekend. We'll be looking through the Shulman tomorrow night as a little
Right.
teaser. But yeah, my mind immediately goes to the University of Arizona Astronomy Club. So I recommend this asker to also check out Astronomy Club. I also participated as an undergrad, and my second week of undergrad, I got to go to the 12-meter dish at Kitt Peak and collect data, which a lot of these science majors, you have to start out with core classes and calculus series, and you don't necessarily get to go to a telescope first. So I will just really highlight that Stewart Observatory within the undergraduate astronomy club really does allow you to go visit. We also did exoplanet projects as undergrads at the, I think it was near the Naval Observatory up there. I think there's something like 20 odd, maybe 16 or so telescopes up on Mount Lemmon proper and Bigelow, so series of telescopes that the students can get access to. And the last plug for this undergraduate, I'll say, check out the NASA Space Grant Consortium. This is a relatively easy application, one page, and often you can request to work with specific centers. So if you wanted to work with Mount Lemmon SkyCenter, you can actually submit your NASA undergraduate proposal, and that's the Arizona Space Grant Consortium. And you could actually work with these optical components or work with different professors through that space grant project. And another follow-up for the center, I know they haven't been running programs, but they do have the new, I don't want to say downtown because it's not on the mountain, but at the base of the Mount Lemmon Highway. Do you want to talk about the new center location?
So there's a store, if that's what you're referring to. Right. Yeah, so that's kind of the headquarters, and it's a store where they have obviously merchandise and cool things to see there. I've been at, this is a while ago now, so I was at the store and I saw much of what they were setting up, though I'm sure it's much better now. And I believe I saw an announcement from Alan stating that they are now open at times. So that would be certainly a place to visit. It is right before you take the turn to go up Catalina Highway. So just check out the store, and you can also look online, I believe, and see some of the things that you can find there. But yeah, buy stuff. That's always a good thing.
Yeah, so this is a plug to really hone in also for our next talk, Flandreau Science Center, Mount Lemmon Sky Center, and Biosphere 2 are all sort of in the hub of the College of Science within the U of A. And the way my director put it to me is College of Science is broke. So if you, supporting these centers, even though it might be like, hey, that's a cool pair of space socks, actually really does go a long way. And yeah, hopefully the online store is available. So another question for kind of the technical side of the astrophotography. A lot of these require different exposure times and sort of finesse. Do you have a master file of 3 seconds worked for this nebula versus 5 seconds? How do you keep track of all these exposures and sort of parameters when you're shooting?
Typically, a lot of the things that you take pictures of are very faint. And usually the game is not to take a short exposure. It's almost always just to get enough signal, enough light, that you have the ability to make those processing choices that I demonstrated in the video. Because if the image is noisy, then you're unable to do much. This is kind of a funny thing about astrophotography, which is that sometimes people think that if an image is noisy or it kind of doesn't look good, then that's more work and you would be doing more processing, but it's actually the opposite. You are given the opportunity, the parameter space to do cool things is greater the more information that you have. So longer is almost always better. You can always just not use some, but that never happens. And the conditions are always variable when you do things in astronomy, so you never have perfect conditions, and so on and so forth. Usually you just take as much as you can. Given the amount of time, that's usually the constraint. It's just the amount of time that you have to collect the information. There are some exceptions. Planets, for example, are very bright, and so you can take pictures of them in very short periods of time. And then the exposure times do matter, but much of my presentation that I showed has what I would call deep sky astrophotography. That's all faint stuff. And that stuff, you need long, long exposures.
So for those, yeah, you pretty much say it's going to be over a minute for those.
Over a minute, yeah. So
several minutes is your first kind of rule of thumb.
So, for example, some of the galaxy pictures, typically a single exposure is 10, 15, maybe even 20 minutes in length, and you end up, gathering 20 to 100 of those exposures in each of the filters. So this takes place over the course of many nights, and then you combine that information, all that processing, to produce the image. And so part of the work is just acquiring the information, but that's actually not the fun part. The more interesting part is once you have it, is how to put that all together and create what is hopefully a compelling image.
Okay. And follow up, speaking of time, the Messier challenge. Have you ever attempted, I know viewing it, there's these, I think it's 111 Messier targets.
Yeah.
Named after a French comet astronomer who had nothing to do with deep sky objects, which I think is fascinating.
He didn't know at the time, he saw them through his telescope, but he just didn't know exactly what they were, other than they were fuzzy and they didn't move.
They were fuzzy and they didn't move, and he made this list of like, oh, don't look at that. That definitely wasn't a comet, right? But it became this kind of this list that this is, something that a lot of astronomers challenge themselves. I know there's star parties dedicated to it, and I'm wondering if you've ever tried to attempt to photograph all the targets in the one night in spring. I believe all the targets are cascade through the whole night.
Yeah. So, when you say photograph, you can take a 1 minute, like you said, a 1 minute exposure of these things. To me, that would not produce a compelling image. And given the state of electronics and computers and everything else, a computer-controlled telescope, it is trivial to use your fingers to tell it to go point here, point there. In fact, you could automate the whole process to observe the Messier marathon in a night and actually go to bed. So I think it loses something of the experience to do a computer-controlled version of that. This is my opinion. I actually am of the ilk where I was observing, back in the early 90s, I did the Messier marathon, but visually. So I know actually where all these things are in the sky, in addition to taking pictures of them. And so, yeah, I stayed up all night to observe all of them. But no, I haven't actually done pictures. Though I will say one thing, a good fraction of the Messier list is not a particularly well-distributed list of things. There are a lot of, for example, of elliptical galaxies that are part of the Virgo cluster, which I pointed out. They're kind of fuzzy, oval. I mean, you take one picture of them and you take another one, you'd be hard to tell the difference between the two. So, no, I haven't done that.
Okay.
Yeah.
It does seem like I agree with your sentiment as, even if you just did these 5-second exposures, you're not, necessarily capturing the detail.
Yeah, I mean, it's cool. Maybe there's a coolness factor, like you caught a little fish or something. I don't know. But, yeah.
A challenge for later times, perhaps. Yeah. Do you recall the very first object that you actually did an astrophotography session on? Or what was your, how did you get into it? Was it one photo or?
It was a photo, yes. My uncle gave me a film camera, and I grew up at a time where color film was the thing in use. So this would have been, let me do some math, 1984, 1985 or so. And I had a telescope at the time. It was an 8-inch Celestron telescope. Maybe it was 86, sorry, I'm doing the math in my head. And the first thing I wanted to do with this camera was not take pictures of people I just wanted to attach the camera to the telescope, and so I did. I knew how to align the telescope so that it would do the best it could. And the first picture, astrophotograph I took, was of the Orion Nebula. And it was remarkable because it was blurry in the sense that the stars were kind of trailed and everything, but you could see the color, you could see some detail. And yeah, that was cool. For me, astrophotography is just another way to share and communicate in terms of popularizing science and astronomy. So looking through a telescope, showing people things in a telescope visually, as well as taking pictures. All of this to me was a way to share. So that picture that I took, I showed people, and that made me happy.
It does. It's the warm fuzzy feeling from showing someone. I'm sure you've been around for people looking through a telescope for the very first time in their life, and there is a very particular reaction, which leads me to the thoughts of how you founded the Mount Lemmon SkyCenter. I know you were involved with astronomy outreach before you founded it via Kit Peak and perhaps Stewart Observatory just in general. Can you talk a little bit about the initiation for that?
Well, since we're here at the University of Arizona, I want to mention that, sure, I studied at the Department of Astronomy at Stewart. And among other things, I was, involved in the Astronomy Club, and I was also one of the telescope operators of what is now the Ray White Observatory. And so I operated the 21-inch telescope. Myself and a few others were very interested at the time in not only using it for that purpose, but also taking pictures with it. So I believe that initially there was a very tiny, it was a guider CCD camera that we took advantage of then. And then Don saw that, Dr. McCarthy, saw that we were interested, and he let us use a slightly better CCD camera, and we played with that until I blew it up once, and he forgave me. So that for me was kind of a beginning of doing this kind of thing. And then beyond that, I did more of those kinds of projects at the U of A that was a way to do, share and instruction with the students. But eventually, after graduating, sure enough, I went to, I found myself in a job at the National Observatory where I basically developed the nightly observing program. Still takes place there. And, but I wanted to expand. I wanted to grow more in this kind of thing of public outreach and develop a program in a way that was different than what Kit Peak is doing. So that for me was the emphasis for the Mount Lemmon SkyCenter, at least the genesis of it. And I approached the right people and talked to the right people and so on and so forth so that these things can happen. I'm very grateful and thankful to all of those people that allowed something like the Mount Lemmon SkyCenter to come to be.
Yeah, that's fascinating that you developed the Kit Peak one, the NOP. I was a guide there too. We call it, we got acronyms for everything, right?
Yeah, and the names were terrible. I got better at names, but yeah.
Got better at acronyms, huh? Okay.
Yeah,
but that's wonderful. I think a lot of people immediately think of astronomy with Tucson, and part of it might be obviously because we can go to the National Observatory when they run programs. Sadly, I just heard that they're all furloughing everyone. So
yeah, this is not a good time for all this. Yeah,
not a good time for astronomical outreach. But we really appreciate it. It's really neat to see that you kind of sprung up two programs on two different mountains around.
Yeah, I've run out of mountains, so
yeah. Maybe when they finally let us do something with that Tumamoc telescope over there in the Tucsons.
I did. Oh, that's another story.
I've heard a lot of people trying. I know Pima County. So we got a question about filters. So are filters worth using in astrophotography? What is your best advice for a beginner in the field of astrophotography? Thank you.
So when you take a picture using a camera and you get a color picture back, there are always filters. When you use a digital camera, the sensor has tiny little filters in front of every single pixel. It's called a Bayer matrix. But usually when you do astronomical imagery, the filter goes in front of the entire chip, where the chip does not discriminate in the different wavelengths of light on its own. It just detects light regardless of what color it is. So to distinguish between the different colors of light, you put filters in front of your sensor, and then you acquire the data, as I showed in the presentation, the greenish light through the green filter, the bluish light through the blue filter, the reddish light. And then later on the computer, when you process the data, you process the images and produce the pretty picture. So the answer to the question is, there are always filters. Yes, they are necessary. They're mandatory if you want to create color images.
Yes, and this is a plug for if folk want to see and tune in on Sunday. We'll have the TAAA, which is another big astronomical outreach endeavor, the Tucson Amateur Astronomy Association. TAAA is going to be using solar filters, and we'll be looking at the sun, specifically a hydrogen alpha filter, where we can actually look at solar activity, even though the sun is quiet. Although, given 2020, I don't know if we want a solar activity abrupt kind of happening. But yeah, if you want to learn a little bit more about how the sun looks in different filters, tune in with us Sunday. We've got time for one more question here, and this is similar to the exposure time thought, but this is a little more specific. Yeah. How do you decide exposure times when you are trying to image a faint nebula, but there are bright stars in the field of view?
Oh, that's an interesting question. So I just wrote an article about this. The article will be published in Sky and Telescope, and one of the things that I happened to mention in the article is the answer to this question. When it comes to producing an image, you do have to, at some level, make a choice as to what you prioritize. So if you have a faint object like a galaxy, and you want the galaxy to be the thing that you're going to look at, some of those processing choices may not be optimal for stars. And I accept that. So the answer is that I wouldn't want to, at the expense of being able to show the galaxy, which is faint, to just make sure the stars look good, if you will. So in my pictures, for example, it's a style thing. Astrophotographers who do this, they can identify everyone's pic. I can tell you, if you show me a picture of someone, I can say who took it because of the style. My style often is, when you look at pictures of my stars, they'll be very bright, and they tend not to have a very saturated color, certainly not in the center. And that is part of the decision that I made, that the contrast and the brightness of the faint object, if it's a nebula or a galaxy, I need to process that, and that comes at the expense of stars if you have this love for saturation of colorful stars or something like that. So the answer is, yeah, you have to choose what to do, and that's a stylistic, aesthetic decision that needs to be made.
Whether you want to show off the nebula or the stars.
There are ways to do both, but there are you won't be able to get everything. You can't have your cake eat it too. Whatever silly cliche you want to use, there are going to be consequences of making some of those choices. Yeah. That
applies in astrophotography as well. Yeah. Okay, and I'll just wrap up with a few of the comments that everyone was saying. Gorgeous work, Adam. Adam is the best. Your work is amazing. So we really thank you. We're going to switch over next to Flandro, so we'll let you go, Adam. And thanks again. We'll look for you on the APOD.
Yeah, and check out the video that Allison put through YouTube. It is available on my YouTube site, so if you'd like to see it in the high resolution, HD, whatever, and with a nice sound, please go visit it there as well.
Yes, Adam's YouTube, our Art of Planetary Science YouTube, and this is a plug for any of the artists that are tuned in, which will be featuring Adam. We're going to have a new artist spotlight page on our TAPS website, the Art of Planetary Science website. So we'll feature works and these types of videos and more in depth from all of you artists. So stay tuned for Artist Spotlight, and thank you again, Adam Block.
Bye-bye. Good night.